Good day everyone. So now we'll discuss about how to interface LCD with the 8051 microcontroller. So before getting into the program, we just have to understand how the LCD is being connected. So we'll use this particular diagram. So this sorry, this particular diagram gives you a simplistic view of how your 8051 microcontroller has to be connected with your LCD interface, that is the LCD screen. So here what I'll do is I'll be using the port 1.0 to 1.8, the whole port 1 for connecting it. I'll be using this one to connect to DB7 to DB0, that is the data bit 0 to data bit 7. So P1, so totally allotted for the data bit, and P0.2 I'll be using it for register select, P0.1 read or write, and P0.0 for enable. So these are all like control signals, while this one is the data bit that I'm going to transfer to the LCD screen. So here we'll see what is the register select function. So in case when we are transferring the command to the command register of the LCD does have different commands like clear screen or start in the left, start in the right. So those things we'll have to give it in the LCD screen. So to do that, we'll have to access the command register. So when if you want to access the command register, we'll have to give the register select signal with 0. And in case when we are writing with the data, that is like whatever the character that we want to print in the LCD screen, so we'll have to access the data register. So whichever the register that we are accessing, according to that we'll have to select the register in the RS signal. So RS signal is P0.2, we'll be accessing accordingly, whether it is a command register or data register. So coming to P0.1, so if you want to read data from the data register or command register, you'll have to put 1 in the read write signal. So in case if you want to write any data, so you'll be using 0. As far as the program that we are going to do, we'll be writing the data only, we'll not be reading anything. So in case if you want to read the status of the register, then you'll be using the 1 in the read write signal that is connected with P0.1. So you can clear this port P0.1 to read the content into the accumulator. Then E is the enable. So this enable pin is connected to P0.0. So now let us get into the program, and we'll come to the commands whenever it is necessary. So this is the program. So I am starting with the assembler directive org0000h. So this makes the assembler to start the program from 0000h. So in case if you want to use some other interrupts, this can be kept as the starting memory address. We need to keep it with at least org 1000h, because the initial part of the memory is being allotted for interrupt service routines. As far as this program is concerned, we are not going to have any interrupt service routine, so I am starting it with 0000h. So org is an assembler directive. Then what I am doing is mov a comma hash 38h. I am moving 38 into the accumulator, and I am calling the command write subroutine. A call command write subroutine. So in command write subroutine, you can see the 38 is moved in the P1, and what I'm doing is in P0.2 I'm making it as 0, so that register select selects the command register, and here CLR P0.1 read write signal I'm making it 0, so write option is enabled. Then set bit P0.0 and clear P0.0. This is like high to low. So when you make high to low in the enable signal, your LCD screen gets enabled. So here 38 signifies some command. So we'll see what 38 signifies. Here 38 signifies that I am initializing the LCD screen as 2 lines and 5x7 matrix LCD screen. So for initializing that, I am using this 38. So these are the command codes for LCD. So you can have a reference of this one whenever it is required. So After completing the command write subroutine, it comes to a call delay. So whenever your LCD screen is being accessed for putting anything into it or reading something from it, it takes some time. So to give that a time delay, we are giving this mov r3 comma hash ff, mov r4 comma hash ff, mov r5 comma hash 55. So loop within a loop structure. We have seen the same kind of a delay earlier. So this delay will give sufficient time for the LCD to uh, obtain the command and register it. So after it has done, then it comes to the main program again. So after command write subroutine and delay subroutine, it comes to mov a comma 0h. So this is in the next command. So next command 0e, e represents display on and cursor blinking. So we are making the LCD to make the display on and blink the cursor. So again, after doing after moving the content to A, the same command write subroutine is being called. So again the same A is put in P1. So from P1 it gets into the LCD screen. Then again register select, I am making it as 0. So to access the command register, CLR P0 0.1 to make the read write signal to go to 0, so that write option happens, and set bit P 0.0, so that high is kept in P 0.0. Then you make it as low, so that enable is activated for the LCD screen. Then again I am returning back. Then again the same a call delay. So delay subroutine gets executed, so that it gives some time span for the command to get registered. Then mov a comma 01h. So 01 represents clear display screen. In case if in the previous operation, if some value has been represented in the screen, so that has to be cleared, so that it doesn't show some garbage values. So for that I am moving 01 to A, and A call command write. So A is moved into P1 port. Then P0.2 is made as a 0 to select the command register. Then clear P0.1, so that write option is getting enabled, and set bit P0.0, so high to low to make the LCD screen get enabled. Then 06 represents increment cursor, shift cursor to the right. So whenever you are putting a new letter, so it should come in the right, and your cursor should go to the right. So to represent that, we are putting this 6. So 6 is has been put, and in the same way I am calling the command write subroutine again. So 6 is transferred to the P1. P1 is put into the command register using this by clearing P0.2 and 0.1 for writing, and P0.0 for enabling the LCD screen. Then again it returns over here, and it calls the delay subroutine. So delay happens, and it comes over here again, mov a comma hash 80h. So again 80h represents force cursor to begin to first line. Basically there are two lines in the LCD screen. So when you want to have things, you want the things if you want your characters and letters to be displayed in the first screen, you will put it as 80. In case if you want to go for the second line, you can make it as C0. So as far as this program is concerned, I am using only the first line. So in case if you if your first line is over, or if you don't want to represent in first line, you can you can always use the second line for representing the next statement or something. So using this C0. So 80 and 80 I am moving it into the P0 using this command write subroutine. P1 using this command write subroutine, and the CLR P0.2 register select, I am selecting the command register, and P0.1 read write, I am making it as a 0 to write the content, and set bit P0.0 and clear 0.0 to make it like high to low. This is command write. Then again delay. Then after that, sorry, here a call delay. Then after that, now I am getting into the data write. So these are the commands that I require. So in case if you want to do something else, obviously you can access this command codes, and using this command codes you can go for doing whatever you want. You can make the you can make your content or your text to scroll, or maybe go in first line something and second line something. So anything, go in right hand direction or go in left hand direction, anything you can do using this, and using proper looping. So these are the commands, and after the commands what I'm doing is, I am moving a comma hash within quotes v. So this v will be represented as a ASCII code. So that is the job of the assembler. So when I am putting a character inside the quote and I am moving it like this, automatically the v will be converted to its equivalent ASCII code, and that will be transferred to the accumulator. So LCD screen can get the ASCII code and print the corresponding character. So when I am representing it within the quotes, obviously here when it gets into the accumulator, it gets into like a hexadecimal number, which is the equivalent ASCII code of v, and that is transferred into the LCD screen, and in the LCD screen it converts the ASCII code into its character. That's the basic idea of LCD screen, and it's a basic advantage also. So with a single data, I can represent the any characters. Movie a comma hash v, and again here I am going for a different subroutine, that is a call data write. DATWRT is the data write, and so in data write you can see I am moving the ASCII code of v into p1. So it's a 8-bit, so total 8-bit will have the hexadecimal value equivalent to the ASCII code of v, and then I am set bit p0.2, so that register select is made as 1. So in the previous case it is 0, now it is 1 to access the data register, and CLR p0.1. so because in this case also I am writing the data into the data register, so it should be 0. And set bit p0.0, clear p0.0, that is common for both command write and data write, wherein you make the pin to go high and to low, so that the your enable pin is enabled in the LCD screen. So after doing this, I am doing it with I. So I is moved, I in the sense the equivalent of ASCII character of I is moved into the accumulator. Then I am calling the data write, and a called delay. So delay subroutine is called again. So in this case also, when I am moving v data write, so delay is there. So delay invariably it has to happen, either you are calling the data write subroutine or data read subroutine, or command write or command read subroutine. Whatever the subroutine is there, you need some delay for accessing the LCD screen. So after this delay, I am putting the equivalent ASCII code of I into the A, and that I am transferring it using the data write subroutine from A to P1, P0.2, RS, that is register select is 1. So data register is accessed. CLR P0.1, so that write option is enabled, and set bit P0.0 and clear P0.0, so that P0.0 shows a high to low, so that your LCD screen is enabled. Then again a call delay, so delay happens. Then I come to T is equivalent. So here I have used everything in uppercase. In ASCII it has a different code for uppercase and a different ASCII code for lowercase. So whatever the things that you are representing over here, the same thing will appear in the screen. If you are putting in uppercase, in screen also you will get it in uppercase. In case if you are putting it with lowercase, in screen also you will get it in lowercase. So T is the T is equivalent ASCII code. I am moving it into the accumulator. Then I am calling the data write subroutine. In the data write subroutine, I am moving the content of A, that is your equivalent of T register, into the P1. Then set bit P0.2, so that your register select is selecting the data register, and clear P0.1, so that write I am making it as a write active. Set bit P0.0, that is high, and I am making it as low using CLR P0.0, so that my LCD screen is activated, enabled. So after doing that, I am calling again the delay subroutine. Then that's the end of the program. So again and jump again, I am coming and staying over here. In case if I want to rotate it or do anything, I'll be having it as a loop. So since I don't want anything else, I just want to print the character in the LCD screen, I'm stopping with the statement again and jump again. So here itself I am stopping it. So this is the whole program and its explanation. After doing the program, you can translate to check whether you have any errors or not. So after doing that, click on this options for target and 11.0592 just make it, and you'll have to click this use on chip ROM, and in the output click create hex file, and your name of the hex file will be created in the name of the project that you have created. So in case if you want to check where it is getting saved, you can click this select folder for objects and you can navigate and check. So it is in my folder objects. So after doing this, again you'll have to click translate, build and rebuild. So then only your hex file will be created. So this hex file you can dump it into the LCD screen. So as far as simulation is concerned, you can have an LCD screen. In case if you want to check anything, you can use the port P0 and P1, wherein you can see the values getting changed. That's it. Other than that, basically you don't have the option of an LCD screen appearing in this software. You can see. So now I am doing. So after things have happened, so whatever it is displaying, the last values that it is showing. So probably the output will be much more clear when we see it as a text in the LCD screen. So now let us get into the hardware connection.
Doing the simulation, so you can click on these options for target and make this crystal frequency as 11.0592. Click use on chip ROM and click output. So here you are supposed to click the create hex file, and here the name of the executable file will be first. So you can navigate and check where it is getting saved. So it is in the folder objects. So after doing this, click this translate, build and rebuild. So first dot hex has been created. So open the flash magic, click options, advanced options. In the hardware config, check that it should be unchecked. Click OK, click this erase all flash and verify after programming, then browse and click this first dot hex, click open and click start. So now I'll be pressing this reset button. So my code is getting dumped. So once the code has been dumped, I'll be connecting this P1 file to DB0 to DB7, and from port 0.0 I'll be connecting to the enable, and 0.1 I'll be connecting to register select, that is read write signal, and at last 0.2 to the register select. So this is the connection that I have made. So I'm pressing this reset. You can see over here the V8 is appearing. So in case if you want to change the pattern, you can change the values and you can increase the number of loops, so to get different words or so. This is the procedure. Thank you.